Okay, so I'm going to start with just a little bit of background with Spongecell to kind of frame the sorts of problems that we deal with and why we care about this kind of thing, the real-time streaming processing. So Spongecell, we basically specialize in dynamic ad experiences. So these are highly interactive ad units built in Flash, HTML5, and in-stream video, so embedded into something like a YouTube video that react to dynamic signals. Like the location, the weather. There are third-party things that we bring in as well, custom signals from our clients, et cetera. And when they're running, since they're so interactive, they're actually tracking a stream of engagement information as people around the internet interact with the ad. So of course, there's the usual impressions, which we usually call hits, and clicks on the ad, which take you somewhere, but also there might be a map embedded in the ad. So we track people interacting with the map for, say, a car dealership, a car company where it has dealership locations or something like that, or hover over information, configuration information. You can do things like book flights in the ads, that sort of thing. So we have that all streaming to our back end in real time for a variety of reasons. Especially these days, conversion attribution information. So, what were people doing with the ad before they converted? Right now, we have a reach of about 100 million events a day, 3 billion events a month. But it's a very shock sort of business, the online ad inventory. Some of it's predictable. We have definite seasonal increases around end of month, end of quarter. Q4 is usually huge. So we are spinning up extra machines to deal with that right now. But there can also be unplanned shocks, big push events by advertisers that can generate a huge load. So we could walk in the morning and have our load double over, in the space of an hour. So that kind of data drives everything in our business, right? It's used for billing. If an impression happens and we don't record it, it doesn't really matter. We eat that cost. So we want a very robust system for moving our data around, and we want to do it quickly. There's lots of different consumers of the traffic. All those interactive dynamic signals, are different consumers of the traffic. We have lots of reporting analytics backends on our side to give information to our customers that all want to consume the data, and they'd all like to do it with relatively low latency because advertising is a very low latency business. And the real-time part really comes in because the advertising world is such an interconnected business. There are lots of moving parts, lots of different companies involved in any single ad view. Adobe had a great little infographic, motion graphic thing that they did a few months back on how an ad actually gets served, and there were at least 4 companies involved in that process. So we try to stay on top of a lot of that so we can inform our customers of when things are happening in a real-time basis because, something gets trafficked incorrectly or a site goes down or a video becomes unavailable. We'd like to know about that. So it's a lot like a systems monitoring sort of application that you might get from, traditional IT. So, but instead of, system load and disk usage or what have you, it's business events, right? It's things that are happening in the business. And when I was at LivePerson, that was a lot of the same sort of thing. People were interested in the conversations people were having in real time so that they could respond to trending topics or changes to policies and get that information distributed to their call centers so that their call center operators could actually respond to that in real time. So that's basically why we care about this sort of stuff. So our stack at Spongecell, and also, this is also similar at LivePerson, I was involved with both, so no surprise there, is Node.js. We also do some Ruby on Rails at Spongecell with jQuery and D3 used for our visualization. So at Spongecell, our edge servers are actually written in Node as well, and they write to Kafka. And then to push data out to things like our dashboards, we tend to use server-sent events and possibly WebSockets. I tend to use server-sent events because I think they're a little simpler and they have better fallback for older browsers that don't support WebSockets as well. And then also as fallbacks, XHR, so AJAX calls with polling and JSON-P, although we don't use that very much. For real-time processing, mostly using Storm, which does real-time aggregation, cleaning sorts of things with Redis or Elasticsearch on the back end. I've also used MongoDB in the past, and I believe Justin is still using that in his Zoomdata stuff. So the Zoomdata stuff came up when I was at LivePerson. We were working together on some of these projects. And then for data motion, we're using Kafka. It just seems to be kind of the best tool for the job for us. We're actually using 0.8, even though it's still in beta, to get to the replication features that it adds, and moving to multiple data centers in 2014. So that's one of the big features for Kafka to us, is that easy multi-data center support. Because we are latency sensitive, we do geo-distribute some of our stuff, and we'd like to geo-distribute more to get those latencies down as we go to different availability zones around the world. And these days it's feeding our Hadoop cluster, the Storm cluster, S3, and then little one-off sorts of things. We peel some of it off to our staging environment for testing and stuff like that. So it's a really convenient way for hooking things in and out. So I'm just going to go through kind of a really quick example of how this stack actually works. And we're going to sort of start at the top and head back. So we're going to start with visualization. And honestly, D3 events and server sent events and D3 is an awesome combination. You can do the same thing with WebSockets, but the difference is WebSockets don't actually use HTTP as their transport protocol, so it's much harder to write a shim that works on an older browser that doesn't support SSE because you have to have this protocol that the browser just fundamentally doesn't support. Whereas with server-sent events, it's actually just HTTP, so you can actually simulate it with simple AJAX-type events and long polling or short polling, depending on what you do. It also happens to work on the mobile WebKit browsers, such as Safari on iOS and Chrome on Android. It does not work on the built-in Android browser, which is a little bit weird to me since they're also WebKit, but it is what it is. And the nice part about SSE is it seems to be relatively lightweight on the battery usage size. So you could have these sorts of applications running on iPads and iPhones, and they work fine, and they don't seem to chew up the battery too badly, which is another reason we chose it when we were first developing this sort of stuff. So this is just a little example of how you actually use SSE with D3. So the dispatch part is on the left-hand side here, and since it's a screen share, I can actually highlight and show people what I'm doing, which is awesome. And it's all managed by this guy right here. So built into the browser, there's this object called an event source, which basically just goes out and connects to an endpoint on the actual web server. So the reason we're screen sharing is this is actually a web page you're looking at running in Chrome in this case, and it's being driven by a little node application on the back end. So it's gone out to the ticker endpoint on my node backend and connected to it. And that connection is long-lived, so it'll stay up for as long as the server allows it. But if it disconnects, it will actually automatically reconnect, which is nice, especially in the mobile environment where you have a lot of network disconnection and reconnection. And then all you have to do is you add an event listener for the message event coming off of that event source, and you're pretty much done now. So anything that comes down that SSE backend will get sent to this message event with a data payload. And then you can parse it or do whatever. I use JSON as my transport. And then I don't have it pasted in here for space reasons, but I have a list of observers, people who want to listen to different channels we can listen to. So I tend to break my things up into channels so that I can pipe different types of events over the same event source flow just to have fewer connections. And then I basically use jQuery to trigger a custom event, data : something, with the proper payload and sent to the proper channel. And then on the client side, we can bind to that over here. So in this case, as you can see down in the little animation, so this thing is live, and this code is actually running. We're sending out a history object or a history dictionary with a little bit of data in it. So over here we split it up into history, and then transmit that out as data : history. And so now we're getting the data and the event across, and we're using a little bit of D3 to render this. So this is SVG down here in the corner. So we've got a DOM element with SVG, and then select all selects DOM elements, and then we bind that to our data, which is how D3 works. We'll get to kind of what all this means in a second. And then we have kind of three things we can do. We can add things, we can modify things, we can remove things. So we go in, we add things that we don't have yet, and then we update things that we already have. So to get a little bit more into detail on this, we'll go through the shortest D3 tutorial ever. So it works a lot like jQuery, but it's focused on this sort of data join. So you saw we use select all, which selects DOM elements, and then data, which effectively joins an array of data, JSON or whatever, to those DOM elements. And then at the end, your join is in one of three states. You have stuff that's in the DOM and in the data. So there we can just use R, which is what we called our join before. You have things that are in the DOM but no longer in the data. They've gone somewhere. The data's gotten smaller or something like that. So if you want to access that part of the Venn diagram, you can use r.exit to specialize on that. And then you have not in the DOM but in the data, and then you have r.enter. So you saw we r.entered, and then we appended elements. So we added new elements to the DOM to match our data. And then for the rest of the elements, we just used R directly to update the elements we already had. And then once you have that selection, you manipulate the attributes in the style, which is optional animation. So on the previous slide, you saw that transition call. So that basically sets up the fact that we're going to do an animation. And that's controllable. So the default is that little sort of easing motion you saw. But there are other options for the tweening process for those of you who are into animation. It's not necessary. You don't need to use it. It just makes things look a little nicer as you get that visual flow from state to state. And then you can modify the attributes with the ATTR function or styles with the style function. So in the last slide, we were calling a position function, which just made it a little bit easier since we were repeating ourselves essentially with the enter and with the updates. And you can see here I have the code for that position function. So when you do a .call, it basically binds it to the selections. We can use this to update the attributes. So here we update the X and Y position based on the data as well as the height, and we set the opacity to 1. Just initially, they're all set to transparent. And then the end result is that little bar graph you got moving around. And there are some higher level things to help you build more complicated graphs than that, as well as some third-party libraries that sit on top of D3 to do fancier graphs and fancier animations that would be tedious to set up. But this is sort of the basic of D3, and that's all you really need to know to get going. That and different DOM elements. So the rest of it is all SVG specific, right? Creating rectangles or circles or what have you. But that was all sort of built into the app. To get information to the app, I tend to use Redis is it provides kind of a nice persistence layer with relatively fast access times, as well as a pub/sub environment for my web sort of applications. So in this example, what we're doing is we're basically setting up another endpoint. This one's called Ticker2 in the Node app that connects to a Redis backend to get pub/sub information. So here's the Redis client in Node, and then we use the onMessage event to put us into publisher sub to listen for events coming over the pub/sub channel, which is just a thing that Redis has. And then when we get information over the pub/sub channel, we basically just take it and push it back out over the socket, just like we were doing before. And then we subscribe to the channel itself. And you can see that functioning down here. So I just have, like before, I just have a little SSE connection in this client that is grabbing information as it's being pushed out over the pub/sub channel. So I have another generator running elsewhere that is pushing to a Redis, and then that Redis is passing on to me. The usual mechanism for this in production apps is that Storm is sending pub/sub events to us to tell us which keys in Redis it's updated, and then the actual application will go out and grab the information from Redis based on what comes over the pub/sub channel to be updated, and then sends that on. So we usually don't use the pub/sub channel directly to transport the data. The data is persisted into Redis, and then the notification of its update comes through pub/sub. And we can see that in this a little example for being driven by Storm. So this is just the basics of what we use for processing, and also the shortest Storm tutorial ever. So the logical architecture of Storm, for people who haven't used it, is a cluster-based processing environment, kind of like Hadoop for streaming, if you want to think of it that way. It's not exactly that, because there's no such thing as a mapper and a reducer in a streaming environment, really. But there are these units of processing, which they call bolts. And then you have these things called spouts, which are basically data ingestion components. So they pull data in from outside sources. For example, Kafka is one of the more popular sources, but you could also use Flume, Redis, any of these other things, wherever your data happens to be. I suppose you could even use MySQL if you wanted. And then you glue them together with something called a topology, which basically just describes how bolts and spouts pass data back and forth to each other. And these are hosted on a physical architecture that is made up of a number of supervisors, which are tasks that run on machines that manage the running of spouts and bolts of a topology. So they're sort of like the task tracker in Hadoop, if you want to think of it that way. And then you have the Nimbus server, which manages which supervisor gets which bolts to run for a topology. So you can think of it as like the job tracker in Hadoop, but for Storm. And it uses Zookeeper to manage all the coordination, so you need to have a Zookeeper cluster around. It's pretty light-loaded since it only uses it for coordination, not for any sort of message passing. Traditionally, Storm has used 0MQ for its message passing, which can be kind of a pain to set up sometimes. But the newest RCs for 0.9 actually use Netty as their message passing. I haven't had a chance to try that out yet, but I'm very excited to not have to configure 0MQ anymore. And so if a supervisor dies, the Nimbus will go out and redistribute spouts and bolts on the remaining supervisors to keep things running. So that generally works pretty well. And if the Nimbus dies, which it doesn't do very often, but sometimes it does, your existing topologies continue to actually work just fine. You just can't rebalance. So if you can get the Nimbus up pretty quick, you can get your rebalancing back, but it doesn't actually bring everything down. So no real single point of failure, which is nice. And so the basic recipe we use is we have a Kafka spout that pulls stuff in from Kafka. And then that drives into parsing bolts, which take the JSON format that we use on our end nodes and transforms it into sort of useful internal Storm tuples. So Storm has this notion of a tuple, which is basically just a typed array that it passes around. And then for different event types, because we have impressions, we have streams, things like that, we produce different streams out of the parser bolts, and then we have other bolts to aggregate stuff into Redis or other locations. So they use different aggregation granularity, so 5-minute granularity, hourly, daily granularity. And then there's an update thread that runs, in our case, on a timer to push events up into Redis. So we do some minor aggregation at the bolt level, and then we push stuff up into Redis. And this just keeps the Redis load a little bit more manageable. Since when an ad is actually being shown, there tend to be a lot of events for that ad in a very short time period, because that's when the ad's being shown. So we can aggregate those a little bit more easily at the low level and then push it up. You can also use tick events to do this, which are a relatively new Storm feature that got added in 0.8 that send a special event called a tick down that you can use as your update indicator instead of a second thread with a timer. But since the code already existed, kind of stuck with the timer stuff. And that implementation kind of looks like this. So here's, for example, a word count, everybody's favorite demo, and at LivePerson, actually pretty useful, since most of the information is actually chat, and so you do want to tokenize words and draw clouds and things like that. If we had like a word count thing, this is our timer to update word count information for the various words coming in from a stream. So you can see here it just runs in the background every second, and there's a hash set of words that have come in from the bolt while the timer task was sleeping that we pull out, and then we go through and we add each of these counts to a Z list in Redis, which is a set with scores on. So we keep the scores in there. And keeping it in a set like that in Redis means we can get things like the top 100 words and stuff like that, so it makes rendering a little bit easier. That bolt itself is here, so you can see it splitting things up and doing some Z adds for the words with timestamps itself. This is for a slightly different application, and then also updating the update. So the bolts that you tend to write for these sorts of things are really, really simple, right? They do a little bit of work, and then they move on. Storm actually also has topology DSL called Trident that will organize these bolts more efficiently, so you can keep them small, but not necessarily pay the cost of network transport if you want. Now, that's not in this example because it's a bit of an older example, pre-Trident, but for modern versions of Storm, you can use that. And then finally, we either report an error or acknowledge that the input happens. So Storm has this notion of transactional processing. So by acknowledging, we can say, okay, we actually have handled this information. Everything we need to know about it has been sent to where it needs to go, and we don't have to try it again, because Storm will retry if it does not get acknowledgement in the transactional setting. And then finally, we have to stick it together. So this is where the topology construction comes in. These days, people tend to use Trident more because this gets a little bit inconvenient to use when the topologies get large. But here we just have the basic topology. So there's a thing called a topology builder, and then we set a bolt called events to that parser bolt we were just looking at. And the shuffle grouping tells us how to partition the data. So that's sort of the equivalent of the partitioner in Hadoop. In this case, we're just shuffle grouping, which means we have no specific partitioning to bolts. They just get randomly updated. And then the other option would be something like a field grouping, where we could make sure that for a given word, it always went to the same bolt, which in aggregation settings makes that a little bit more efficient. And then we have our tokenizer bolt, which is the one we were just looking at, that actually splits the words up and sends them up, and we actually configure Redis here. And we just shuffle group that from the event parser bolt, which is parsing out different wine events and passing them to the tokenized bolt. So that's what this shuffle grouping says. It says go back to the events bolt and grab the wines output type. which, as you recall at the very beginning, we produce different types by different output types, each in their own separate stream. And then off you go. And actually, on that note, I will pass it off to Justin because his storm-based demos from Zoomdata are way more awesome than mine.
Thanks, Byron. Thank you very much. Let me turn on my screen share here. Perfect. So what I'm going to show is Byron showed a lot of the underlying technical components of how to hook up Storm and D3 to do data visualization. We at Zoomdata have been using these technologies for the last year and a half or so to build a next-generation data analytics and visualization platform based on those technologies for real-time big streaming data. And I'm going to show you a little bit about how these technologies can be put together into a real production application. And this can either serve as inspiration for things that you guys build using these underlying technologies, or you're also welcome to try out the Zoomdata platform itself to hook directly up to your data as well. So I'm going to talk a little bit about the architecture that we've put together with Zoomdata and then show some demos, as Byron mentioned. So in general, in Zoomdata, we're connecting to real-time streams of data as well as historical sets of data. And Zoomdata has a variety of connectors, and I'll show in a second where those are actually set up. But the processing in Zoomdata that we do involves kind of three stacks of technology. The first is on the data connector side. And here's where we connect to both real-time streams of data as well as historical data, because a lot of times people want to see their data in real time, but they also want the ability to kind of rewind and see historical data as well. So we've set up a variety of connectors to queuing technologies like Flume and Kafka, as Byron mentioned, as well as other things that can pull the data in through Zoomdata in real time. And also we have connectors to things like Cloudera, Impala, Solar, as well as traditional databases, Redshift, places people tend to keep historical data. So we're very pluggable on the connector side to be able to kind of easily connect to those things. The data then is put through our data switch, which switches between real-time and historical data based on what users want to see. And then we use our stream processing engine. And we're doing data visualization and analytics a little bit differently than it's traditionally done. Most legacy business intelligence tools will generate a big SQL statement and run it against Oracle or a Teradata and wait between 2 and 20 to 200 seconds or so for the result to come back before showing it to the user. We use a different approach based on the Storm stream processing engine, where we take the streams of data real time and we do continuous math across those streams, kind of like continuous event processing, but really geared more for analytics. And I'll show you what those look like in a second in our demo. And we use that not only for real-time data, but also for historical data. So instead of launching big queries and waiting for the results, we run streams of little tiny queries against historical data, and we process the results of those micro queries, as we call them, also through the stream processing engine. So that allows us to very quickly visualize very large sets of data, but do it almost instantaneously. And on the visualization side, we're using the D3.js visualization library. And I'll show you how you can take any of the D3 examples and plug them into Zoomdata. And Zoomdata uses the Storm and connector approach to light up a D3 visual with real-time data and to make it interactive. And on the interface side, we're really focused on kind of touch-first, mobile-first interfaces while still supporting web browsers. We're very interested in next-generation interfaces like gestural computing, even augmented reality, and bringing data analysis to those types of computing platforms and user interface platforms. So installing Zoomdata is very easy. You can download it directly from our download page, either as a Linux installer or as a virtual machine. And it's possible just to go ahead and download it. And once you do that, you see the Zoomdata sources page. And this is where we have the connectors to the real-time and historical data sets. So the simplest way to feed real-time data into Zoomdata is just to send arbitrary JSON or XML to our HTTP endpoint and just really stream the real-time JSON data to Zoomdata as it's coming in. And if you do this, Zoomdata stashes it in a temporary data cache, which is, as Byron mentioned earlier, in a MongoDB. And we use that to kind of hold data that comes in through the direct connector. We also have a Twitter connector, which can be used to connect directly to the Twitter stream or filter API. We also have connectors pre-built with DataSift. DataSift, if you're not aware, has 200 different social data sources that you can purchase. And we're set up directly to receive data from DataSift directly into Zoomdata. trying to make it just very, very easy to get data into Zoomdata from real-time sources as well as historical resources. Hadoop HDFS systems with the Cloudera SQL on Hadoop, Impala system, for example, Solar, which is Cloudera, has wrapped as Cloudera Search, as well as Amazon Redshift, Splunk, other places, and as Byron mentioned as well, LivePerson, we're hooking up to their API. So it's pretty easy to hook up to these kind of sources, and when Zoomdata is hooked up to one of these sources, it automatically just reads the fields from the underlying data system, in this case, for example, and just recognizes what fields are available. So the goal is to make this very easy to point to data sources, all the different types that Byron mentioned, to feed data in real time, as well as to look at historical data. And once it's connected to those sources, the end user starts to interact with D3.js visualizations. So the first visualization they'll see actually is a visualization showing the different data sources that they've connected to Zoomdata. So here we have each data source represented as a little planet of data. You can see some of these sources are spinning around, and these are ones where data is actually flowing in real time. The ones that are not spinning are ones that are just purely historical data sources. So we have an example data source, which is real-time retail sales data. And to see that, I can just zoom directly into that source and get to a data visualization that shows me the data analyzed in a very traditional visual. In this case, it's obviously a bar chart, and these are all rendered by D3.js. And if you notice, these little bars are growing and shifting around and changing color slightly as time goes by. And that's based on this real-time rolling window. So the data here is based on a real-time 1-hour rolling window that's continuously sliding to the right. And users can interact. They can change the time frame. They can look at more historical data. Or they can just, if they want to rewind, use this time bar we have on the bottom. And this really provides a kind of a DVR-like interface. And again, this is all powered by D3.js and by Storm-like technologies. And as I'm fast-forwarding now through historical data, you can see the real-time historical data is being run through the stream processing engine and fed directly into the D3 visual and updating as I'm fast-forwarding. And then when I get back to the live point, it just snaps back to the live data stream and stops fast-forwarding. So to interact, users can touch our data attributes, and this just reads the data fields that are coming in through the JSON or coming in from the historical data. And they can, what we call finger paint with data, just touch any of these data attributes to shift the display from one thing to another. Or they can even do what we call finger painting, which is where they can grab one of these attributes. And these are all just nice little D3 objects, and users could grab one of these little data attributes and drop it on top of another attribute in order to drill down. We also make it very easy to leverage different D3.js templates. We've built a bunch of them that come with Zoomdata, and then I'll show you how you can build custom and plug in custom D3.js visualizations as well. So in this case, it's very easy for users to switch to a pie chart. And one of the cooler things we've done is build something that compares real-time data with historical data. We call it comparison mode. And what this does is it takes the real-time stream and does stream processing off the real-time data and shows it in the foreground bar. And then we also have a background bar also drawn with D3, which is showing the historical data, in this case from yesterday, but during the exact same rolling window. So this lets users visually compare what's happening in real time to what's happened historically and really visualize those deltas. So it's one of the kind of cooler uses of the D3.js technology combined with all the back-end stuff we've been talking about. So a lot of users want to see data one thing at a time. Plus also they typically want to see data in a dashboard layout. So we've used something called Gridster, which is a JavaScript framework that allows us to just very quickly put different visuals and let users arrange different visuals on the screen in a dashboard type view. So they can really see data however they like. And then they can rearrange it. So if they want to move these little windows around, they can just grab the header and they can move any of these little widgets, and they kind of get out of each other's way. So that's what we're trying to do, is make it really easy for people to create visual dashboards from scratch based on real-time and historical data. And one view I use a lot myself is the Twitter data. So I like to look at, because I'm in the big data industry, I like to look at what's happening in real time on Twitter on big data topics. So I use this dashboard, which takes in all the tweets that are happening in real time about big data, and I can see real-time views, including the number of tweets that are happening each minute. So it's 1:39 Eastern right now, so as any of you, if you go tweet about any big data topic, this little green bar on the edge of this time trend will grow every time a new tweet comes in. And that's coming directly in through a stream, through the stream processing, and feeding through WebSockets directly into this D3 visualization. And also we can see data in different visuals. For example, word cloud, as Byron mentioned, showing word clouds is a great way to let users kind of just see what's going on. In this case, I'm looking at a word cloud of all the hashtags. And if I'm interested in any of these topics, I could just touch one of the words or one of the bars and go and see the raw data. So pull out and go view the actual raw tweets. And from here, I oftentimes will go and link to the actual tweet and sometimes respond or retweet to some of these things. So really, what normally would be a massive just stream of Twitter, really these kind of dashboards, at least for me, help boil it down in a very convenient way. So Zoomdata, again, is hooked up to lots of different sources using all of this Storm and D3.js type approach. One of the other interesting sources that we hook up to is Solar for unstructured text, and being able to fuse together unstructured text with structured data is something that's very interesting to me and that we've done some work on. So this dashboard actually shows data from hotel reviews. It's 250,000 hotel reviews. And this is stored in Cloudera Search, which is a Solar-based backend. And you can see I can type something into the search box, like room, and I can immediately see the structured and unstructured data that comes back from that search. And I can, just like my Facebook feed, I can infinitely scroll through the resulting views. And more interestingly, the visuals on the left-hand side are also based on the results of Solar. And as I do a structured search, these little D3 visuals immediately update with the results from the Solar facets. And we even have a little view that shows those facets and let users interact with those facets. So trying to make it just very, very easy for users to interact with real-time, historical, big data, structured and unstructured data as well. One thing that we've done with D3, as you've seen, all of our visuals are based on D3.js. One thing we want to do, and what we've done, is allow any of these D3 examples. If you've gone to the GitHub repository page for D3, you can see there's just hundreds and hundreds of ways that other people have created to take D3.js and apply it to lots of different visual use cases. And this page just goes on and on and on. And when we started working with web-click data, lots of big web-click data, one of our customers wanted to see that data in a couple different ways. They wanted to see it as a chord diagram. So since we have access to D3.js, we found this example that was created by a journalist at New York Times to show flows of European debt between countries. And it's a really, really nice visual that shows a really compelling chord diagram. And the problem is, though, it's not interactive. If I click on it, nothing happens. And of course, the data here is actually pretty small. It's not big data. It's just this little CSV file that's attached to the bottom. But what is very interesting is that the middle part is the actual D3 definition code. And this is about 150 lines of D3 definitional code. And in Zoomdata, we have something called the Visualization Studio. And this lets D3 developers plug in any D3.js example they like and hook it into the Zoomdata framework to allow Zoomdata to kind of power it with the real-time data and make these D3 visuals interactive. So in our Visualization Studio, you can take any of those D3 examples and you can plug the D3.js code in on the left-hand side. And then on the right-hand side, Zoomdata shows that D3.js visual, but powered by Zoomdata doing all that stream processing against real-time data or historical data. So this chord diagram that was kind of static on the D3 example site is now lit up with historical big data. This data is actually stored in HDFS with the Cloudera Impala engine on top of it, and also it's interactive. So I can now touch any of these edges of this chord diagram to explore and zoom in to follow user traffic as they go from page to page. So it's very easy to take any D3.js, plug it in, and then create these kind of custom visuals, make them interactive, hook them up to a variety of different data sources, and then save them so that users can then use them applied to their data of choice. And for those of you who may be interested in more details on that, we have a set of tutorials in YouTube. If you go to Zoomdata's YouTube page, you'll see we have tutorial 1, 2, and 3, and these actually walk through the process of taking a D3.js example from the D3 GitHub repository and plugging it into the Visualization Studio. And there are a couple things you need to do to the code to hook it up to the way Zoomdata pumps the data in and also hook it into the Zoomdata interactivity. But once you do that, you can then have a fully interactive D3 custom and plug it into the dashboards and other things. And the thing I'll show last here in closing before we get to Q&A is that the Zoomdata widgets are also very embeddable. So we, for example, on our Zoomdata demo page, zoomdata.com/demos, we have some of these widgets directly running here on our web page. So we have, for example, some of that real-time sales data showing up. And from just right here on the web page, I can come and I can rewind using that time bar. I can fast forward, just as I did in that dashboard. I could change the type of visualization to a bar chart, to a word cloud, or any other D3. And I can interact with the data however I like and go back and look at historical trends. All the same interactivity available through that dashboard we can do just in this little embedded widget here on the website. And those of you in the big data space, we have that real-time Twitter view as well embedded directly in the website. So you can just launch that demo directly from there. And any of you who want to play with Zoomdata on our download page, you can actually download a virtual machine preloaded with Zoomdata, or you can download an RPM installer for Linux. And then you can do all the things I just showed, hook it up to data, and plug in your own custom D3.js visuals. And we'd love to get anybody's feedback on that. So that's what I wanted to show on Zoomdata. Again, we've had a great time using these technologies, and we think it's really helping us build a really, really great next-generation data visualization product. And so I'll turn it over to questions.
Excellent. Thank you so much, gentlemen, for a fantastic presentation. We do have quite a few questions here. We'll start with a question for Byron. Are you using Trident, Storm, or Plain Storm? Is there the transactional type need that makes Trident important?
It depends on what we're doing. We have some stuff that requires the transaction capability, so there we're using Trident. When I can get away with it, I tend to use just plain old Storm. I don't know. I actually find plain old Storm a little bit easier to use than Trident. But that's, yeah, maybe I'm just old and cranky, having used Storm before Trident exists. So we tend to use, like I said, we tend to use Trident when we're using the transaction stuff, and then plain old Storm in other places. The nice part is you can have multiple topologies, so you don't have to necessarily pick one or the other for a given processing.
Great, thank you. Henrik wants to know, for Byron, does your stream of event have a schema definition of the values in the stream?
Yes. So at Spongecell, we use JSON encoding, which happens to be Avro compatible. So we can use Avro as our schema definition language, and then the JSON parser for Avro. LivePerson is a much older company and predates any of that sort of stuff, but it had its own internal schema that was hosted in Java, because all of LivePerson's stack is Java-based for most of that. So yes, in both cases, and then we introspected those to generate the different streams.
We have a question from C. Bond here. Your Storm examples were in Java. Can you use dynamically typed languages? If so, does it impact real-time performance? With
Storm, I believe you can. I think other people do. I don't, because I've been using Java for such a long time, and a lot of the code that I use comes from Hadoop Java classes, which is already written. But Storm itself is written in Clojure, so you can obviously use Clojure, and I'm sure you could strap Scala to it as well. There's probably libraries around for it from Twitter for doing that, because they use a lot of Scala internally. So both those languages should work right out of the box.
We have another question for you, Byron, from Mo. As the live data is dynamically presented, how is it stored to be accessed or rewind later? Is it a separate thread? Also, what type of schema is the historical rewind data stored?
So for our stuff, the persistent store for the presentation is in Redis. Justin's a little bit different for Zoomdata. But for us, it's in Redis. And then we're actually grabbing the data from the Redis persistence layer when we do the real-time visualization. So we get the notification that various keys in Redis have been updated, and we'll go out and grab them and ship them out to the client. We also, because we're using Kafka, we also have the raw data streamed out to our Hadoop cluster for safekeeping and longer-term storage. And we're actually, Spongecell is hosted in AWS, so we also use a third stream because we're paranoid to store it to S3 in its raw form, so we could always replay it from there if something got screwed up.
And from the Zoomdata perspective, as Byron mentioned, by default, Zoomdata stashes any data that's pushed to it dynamically into a MongoDB to support the rewind. In the case of rewind, we're just restreaming the data from the MongoDB. We also have just added the ability to index any data that's pushed to Zoomdata directly into Solar, and we're able to also do that rewind from Solar as well. And we're working on the ability to integrate with Flume to be able to write the data directly into HDFS Parquet format, which will support the Cloudera Impala architecture. So when the data is truly, truly big, but it's also real-time, taking real-time streams from Flume, writing them in a minute-by-minute fashion into Parquet clusters, and then looping that into Zoomdata is really the best way to handle it, really, really big data. And the question on the schema, in MongoDB, we just store the data in the same JSON document format as it's presented. For Solar storage, we index the entire document and facet it by default on any elements present using morph lines. And for storage in Impala, it has to go down to kind of a table and column structure to do that.
All right. And Justin, Henrik would like to know, would you care to comment on the differences between something like reactive demand programming or reactive functional programming and something like Storm on a distributed level, which is similar to how signals generate events? In your case, your microqueries, aren't they similar to values updated over time? How do you see the future of values time, and how do you handle the compute over them?
Byron might be able to take the first half of that question, but I'll answer the second half. And we treat the microquery result stream the same way we treat a real-time data stream, in that as those microqueries come in, it allows us to initially draw an estimated picture of the data within a second or so. And then as more micro-result queries come in, we sharpen, if you will, the result display. And this is the way, for example, similar to the way YouTube, if you start playing a YouTube video, it starts out kind of fuzzy, but it's watchable, and it starts immediately instead of buffering for 30 seconds like in the old days. But it starts out a little fuzzy, and as you watch it, it gets sharper and sharper. So we're doing the same thing for the historical microqueries against the big data. Byron, do you want to answer the question about the reactive demand programming, reactive functional programming?
I wouldn't say we explicitly use the reactive model. I guess the stuff is kind of reactive in the sense that there are notifications that get pushed out to the clients that then update things. But it's not, I guess I never really explicitly thought of it as a reactive thing. I think of it more as event-driven. I don't think I'm answering the question very well, unfortunately, since it's not really something I thought about.
All right. Well, we can go on to the next.
I'd have to get back. Yeah.
Yeah, me too.
Email, we can do that. We can do that offline in a more in-depth discussion.
Yeah.
Like just tweet me. Yeah, exactly.
Cool.
Perfect. Wan wanted to know, for the bar chat, is the data coming from real-time streaming, or are they fetched from pre-processed and DB stored data?
Yeah, so in the Zoomdata bar chart example I showed, it's all the real-time view that I showed was all based on real-time data coming in. So as those tweets were coming in, for example, each tweet comes in a stream. Zoomdata catches it, and it goes through the stream processing, which I mentioned is a storm-like processing topology structure, and it increments or decrements the counters accordingly, and it immediately pushes out the new value through WebSockets to the D3.js visual, which updates it dynamically. So there's no wait cycles or delays between the tweet coming from the Twitter streaming API through Zoomdata, updating the right counters, and pushing it directly to the visual. For the rewind use case, it's doing the same thing, except instead of coming from the Twitter API, it's just restreaming it from the MongoDB. But the exact same stream processing approach is used. So nothing is pre-processed. The data is stored raw, and we always operate off raw data, even in big data situations through the microqueries. But we don't believe in pre-aggregating anything because that really reduces the functionality and the flexibility for users to be able to filter it and dynamically ask questions of it. So the reason we like technologies like HDFS, Impala, and Storm is that it allows for dynamic, even real-time historical processing in a very flexible manner against raw data without having to put it into structured aggregate form, because aggregation, as everybody knows, slows it down, it kills the real-time aspect of it, and it also limits the questions that can be asked of the data.
All right, and Justin, Mahesh wants to know, what is the JavaScript library for the dashboard?
Yeah, I mentioned we're using in terms of the squares repelling each other, we're currently using Gridster. There's another library called Packery, which is Gridster is open source. Packery is effectively open source. It's $39 or something. But then we've done a lot of work ourselves within Zoomdata to allow for the zooming in and out, and we've kind of modified the Gridster to kind of operate in a very, very interesting manner.
Yeah, we use Gridster for our stuff at Spongecell too. Like all of our internal dashboards are all Gridster-based.
Excellent. And Andy would like to know, is there a large CPU, et cetera, footprint for this real-time data processing, or is a layer available to estimate CPU carbon costs? Maybe efficiency is more of a data science question rather than the visualization by data consumers.
Yeah, more of a data source question. Yeah, the way Zoomdata operates is we try to push as much of the processing to the back-end data source, kind of as the question was asked. So, for example, when we're running microqueries against Impala or against Solar or against a fast back-end like a Vertica or a Redshift, and we try to do as much of the work on the back-end system as possible because, for example, Impala is probably on top of 100 to multi-thousand node in some cases, HDFS infrastructure, which is very, very capable of taking huge numbers of these little tiny queries and running them in streams very, very quickly against really big data. So the real-time layer for Zoomdata, we try to keep it as light as possible by pushing as much of the work as can be done to the back end. However, in some cases where you're fusing together and joining together data from multiple sources, that involves streaming kind of semi-real-time aggregated data through Zoomdata. So there can be some memory there. But in general, we're trying to push as much of it to the back end as possible so that much more power, if you have to choose where to apply the power, we'd prefer you apply it to the back end data storage and the back end data query layers like an Impala or Solar, and then just have enough machines for Zoomdata. And Zoomdata scalability is mostly by number of concurrent users because each concurrent user might be looking at 4 or 8 different views updating in real time on their dashboard, plus each of those views might be pointing to a different time point with a different filter, with a different security credential, with a different thing in the rows and things in the columns. So each user might be generating a whole bunch of simultaneous topologies all at once. And I didn't mention this in great detail in this. I mentioned it during our Strata presentation that we did. But we actually had to move away from using native Storm for that aspect of it because when we had one topology per report running, as soon as you get into a situation with multiple users and multiple reports on a dashboard, we ended up in situations where we'd have 20, 50, 100, multiple hundreds of topologies running or trying to run on a single server, and that's something that Storm is not optimized for. At least it wasn't when we tried using it. We started using it a year ago or so.
Yeah, and on our side, we're in a little bit different situation because we're not multi-tenant. Spongecell is Spongecell, and we have clients, but they don't really operate in a multi-tenant fashion. So we have a very small number of topologies, relatively speaking, but performance is usually quite good, so the hardware requirements are more modest than you'd expect if you're coming from other things. So a lot, so I've had baseline topologies able to push, a day of able to handle, sort of 100 million and 150 million event per day traffic load on only a few machines, 3 or 4, sort of AWS extra large. So for that 4-core, which is not too bad considering the Hadoop clusters tend to be in the 20, 30, 50, 100,000 sort of node range. We can also scale ours up and down depending on load, of course, since we're in AWS.
All right, and just a couple more questions here. Justin, can I put in Zoomdata? Can I put Zoomdata into my custom web application? And also, is it possible to connect to a NoSQL database such as Cassandra from Zoomdata?
Yep. So as I showed towards the end of my demo, Zoomdata widgets can be plugged into a custom web interface or into a portal or into a SharePoint or into a web page, either using iframe or by directly embedding the JavaScript. So that latter option is a little harder. The easiest way is to do it through iframes. The second question about the NoSQL repositories, we have a connector to MongoDB right now, and we're going to be adding a connector to Cassandra and to HBase as well. So if you get in touch with me, I can provide more information about when we'll have those available. And as I mentioned, our connector library is actually extensible by the users themselves. So using the right API, it's possible to connect Zoomdata even without our help to new types of sources.
All right, and last question here. Is Zoomdata open source or licensed?
Yeah, Zoomdata, although we're using lots of open source pieces, is actually a licensed software. However, you can download it freely from zoomdata.com and use it for up to 5 users for free. And we encourage people to do that, to try it out, and to get in touch with us. We'd love to hear people's use cases and experiences using it. So free to download and use for up to 5 users. We do not charge based on volume of data or by number of Hadoop nodes or anything like that. It's a per-user model once you get past the 5 free users. But we're trying to keep it very, very inexpensive and very deployable to large numbers of users.
All right. Thanks so much, gentlemen. That concludes our webcast. Do you have anything further you'd like to add or say to the audience?
The code for this for mine is actually available on my GitHub. If people want to play around with the little node demos I had in the Strata 2013 repo there.
Yep, and I'll add that as I showed and mentioned, Zoomdata, you can play with it at the Zoomdata/demo. You can download it from Zoomdata/download. And we'd love to hear from anybody with their feedback and thoughts. And I'd like to thank Audra and the rest of the conference moderator crew here for their amazing support and preparation for this. And it's been great talking to you about these technologies today.
All
yeah,
right.
It's been a lot of fun.
Well, thank you both so much. That was fantastic and well received. And thank you all, audience, for joining us today. We love it when we have people from all over the world. And again, the webcast will be recorded and we'll have an archive up within 48 hours. So thanks again, and have a good morning, good afternoon, or evening from wherever you're from. Goodbye.
Bye, everybody.
Thank you.
Is that it?